As promised now, today we are going to start hydrolysis. You can say why hydrolysis, because hydrolysis is actually another type of reaction. In previous reactions, we have seen that sometimes some reactions need some help, some input of energy to get them going, like usually we heat the reactants to help them. But this time, instead of heating the reactants, we are going to help them with electricity. So, in other words, electrolysis is a reaction. I prefer this definition, which is not from the book. So, electrolysis is the process by which a DC power, that means like a battery, a DC power supply, provides the necessary energy to cause a chemical reaction, which otherwise might not have been spontaneous. This is done by applying a potential difference across two electrodes immersed in an electrolyte. And below we see the main parts of an electrolytic cell in which the process of electrolysis takes place. So I start this way, in the deep end. Now look at this apparatus here. You see that there is some container containing some liquid, and in this container we have two rods made of graphite. And this is the apparatus in which the electrolysis reaction takes place. And we say the input here is electricity. So what we do here, look at this diagram here. These two rods are connected to a battery. That represents a battery here. And therefore, if we pass an electric current in this apparatus, we cause this reaction that we call electrolysis. Now let us start properly. Let's look at this diagram, which is a lot simpler to put our act together and help us start. Again, we have, you see this beaker, there is something in there, some fluid. And this fluid actually is what we call an electrolyte. Electrolyte, if you have not heard the word before, perhaps from physics, electrolyte is a liquid that conducts. Like we have good conductors, and usually we talk about the metallic conductors, which are the best conductors. Conductors can also be liquids. And when they are liquids, we call them electrolytes. And why is an electrolyte a conductor? If we think of a metal conductor, which we are familiar with the metal conductors because it's this is what the wires in electric circuits conduct. Metals are the best conductors. Metals, why do they conduct? Why do we call them conductors? Because they have free electrons. And if you remember from the metallic bond, we saw where the free electrons come from, and they can move freely within the material. That is why the material conducts. Similarly, so in other words, metals conduct because they have free electrons, which are charged particles, which are free to move everywhere in the material. For the same reason now, some liquids can conduct because they have free mobile, in other words, mobile charged particles, which can move freely. And the charged particles that can move inside electrolytes are ions. They are positive ions and negative ions. And this can, because they are free to move within the liquid, within this volume, this liquid can conduct, and we call it an electrolyte in particular. So electrolytes are conductive liquids, in other words. And why do they conduct? Because they have positive and negative ions, which are mobile charged particles. The secret of being a conductor is to have mobile charged particles. So this is an electrolyte. It's a conductive substance, in other words, which has ions. Okay. So here in this column here, I have some important words that we need in the electrolysis. And as we look at these words one by one, we'll also look at this drawing here, which represents actually an electrolytic cell. This is this apparatus here, it's called the electrolytic cell. And in this electrolytic cell, what happens? The process of electrolysis. Now, you see inside the cell, inside this container with the liquid, the electrolyte, we have those two rods inserted. Usually those two rods are made of graphite, usually graphite, which is like the pencil leads. You know what is inside the pencil that we write? This is graphite. So these are two graphite rods, which we call the electrodes. In particular, they are called electrodes. So these are usually graphite, okay, those two rods. Why graphite? Because graphite is very inactive. It's an inert substance and does not react and interfere with the reaction, the electrolysis reaction that happens in the electrolyte when we pass an electric current. So the reason for the graphite is because it's an inert substance. They are inert electrodes. They're both the same, both graphite. Another type of substance that we could use for these rods would be platinum, because platinum is also inactive, but also platinum is very expensive, so therefore we use graphite. Now, look at this arrangement here. We have this battery. I have no idea where is the positive and the negative, nevertheless, because it doesn't show clearly. But nevertheless, one rod, one electrode is connected to the positive, say this side is the positive, then the other is the negative, say. Well, the one that is, one rod is connected to the positive terminal, the other is connected to the negative terminal, and therefore one rod is called the anode and the other is called the cathode. Let's go quickly, so I want to go to the next page where things are shown more clearly. And in fact, let's go now. Okay, so here again we have a more professional diagram of an electrolytic cell. We see again the container, we see one rod and the other rod and the battery. Here we can see that this is the positive terminal of the battery, so here is the negative. Now the positive terminal, obviously this rod corresponds to the positive terminal of the electrolytic cell, because it's connected to the positive of the battery. So this, the positive is called, this electrode is called the anode. And this, the other electrode, which is connected to the negative terminal, is called the cathode. Oh, here they are, cathode and anode. Here, this is the cathode. So remember, cathode is the negative, anode is the positive, okay, in the electrolytic cell. All right. Now, what happens here? If this liquid now is supposed to be the electrolyte. Okay, here it's electrolyte. This liquid is an electrolyte, which means it has positive and negative ions. Okay, that's the characteristic of the electrolyte. It has positive and negative ions. Once we connect these two electrodes to the battery, the negative ions tend to move towards the anode, because this is the part connected to the positive terminal. Let's make it a little bit bigger because it's too small. Even bigger, actually. I hope you can see them better now. So the kind of the red spheres represent the positive ions. The blue represent the negative ions. There is a sign, I hope you can see it a little bit. So the negative ions, remember electrolytes have negative ions and positive ions. That is what makes them electrolytes. So the negative ions move towards the anode, this electrode which is connected to the positive terminal, and the positive ions moving towards the cathode. And if you remember, the negative ions are called anions. Another name for negative ions is anions, and that is the reason why we call them anions, because they move towards the anode. And the positive ions are also called cations. And now we understand why we call them cations, because they move towards the cathode. Okay, so the cations is from the cathode and anions from the anode. Okay, so this is the principle of what happens in an electrolytic cell. Simply the application of an the connection to a DC power source actually causes the positive and negative ions to move at opposite electrodes. And as they do, they separate the initial substance. Now, what really happens in this process of electrolysis is that we supply electrical energy in other words, because we connect it to an electricity supply, DC supply, of course, must be DC, direct current. So we put electrical energy in, and the result is we get chemical energy out, because the result is a chemical reaction. So electrical energy in, chemical energy out. It's just a transformation of energy in this type of setup. And yeah, in physics, we call this the chemical effect of the electric current. When you place two electrodes in an electrolyte, it splits the ions and cations. Now let us see in more detail different applications of this process where we use the electrolytic cell with particular electrolytes. So the first electrolyte we're going to see now is when we have a molten ionic compound. So this is not now, our electrolyte, this electrolyte now in this electrolytic cell will be a molten ionic compound, which means it's not a solution in water or any other solvent. There is no solvent here. It's just an ionic compound which has been molten. Like in this case, and usually you're going to see this case of this compound, the lead bromide. Where is the lead bromide here? Do I say it anyway? So the compound that is here molten is lead, oh, there it is, goodness, lead bromide, you see, lead bromide. There is a reason why we choose the lead bromide, and it's also in your book and in other books that you're going to see lead bromide. Why? It's a very special compound because, you know, to make a compound, a solid object, to make it molten, we need obviously to heat it up, isn't it? We need to supply energy, heating here, you see, we have to heat it to melt it. And it so happens that any ionic compounds, to melt them, we need to supply quite a lot of thermal energy because they have a very high melting point. They have a very high melting point because the ionic bond that holds the compound together is quite strong. These are all ionic compounds, of course, because we want them to split into the ions, so obviously ionic compounds, that's important. So all these ionic compounds have a very high melting point, so we need to supply a lot of heat. I mean, we need to heat them to quite high temperature to get them molten. But this lead bromide in particular has a low melting point. What is the 300 something? I have written somewhere, but I don't remember. I'll find it. Anyways, 371 degrees Celsius. So 371 degrees Celsius is enough to melt this lead bromide. So it's very convenient to use this as an example. It's less than anything else. So if we heat lead bromide and becomes molten, its ions separate. And once they are separated, they are easy to move, and therefore it conducts, it becomes an electrolyte. So molten ionic compounds are electrolytes. Electrolytes because they have ions that can move. All these are electrolytes. So, okay, so now that the lead ions and the bromide ions split and they are free to move, the solution here, the electrolyte is not a solution, sorry, I shouldn't say. The liquid here conducts. Let me make that clear. This is not a solution. It's just molten lead bromide. All right. So the bromide ions, being negative, move towards the anode. The anions, of course. The lead ions, being the positive ones, or cations, move towards the cathode. And therefore, there is a current here. In fact, it's like any ordinary electric circuit. What is an electric circuit? We have a battery and wires, and we have a load here, and there is, once the circuit is complete, there is a current, the conventional current, and there is a current everywhere the same in the circuit. So this is the load. So in our case of this electrolytic cell, the load is the electrolytic cell. Okay, so it is a conductor. I mean, in an electric circuit, all the parts that make up this electric circuit, from the battery to the load to the wires, everything has to conduct. So the load in this case conducts, but it's not a metallic wire. It's just it's a molten. It's an electrolyte. It has ions instead of free electrons. Now, once it conducts, there is the same current in here, current everywhere in the circuit, like in any other circuit. Remember now, when we symbolize here the current in the circuit, we represent it. This is supposed to be the conventional current, not doesn't show the flow of electrons, shows the flow of positive charges, if there was a positive charge. Here in this diagram, we see the flow of electrons, which is the opposite than the conventional charge. Okay, so the conventional current is in this direction. Just, I want you to understand that the current is the same in the external circuit here in the wires and inside the electrolyte. It's the same current. And this current, the total current, is actually made out of the two currents, the current produced by the anions and the current of the cations. Both, we add them together, and together this the result is the same current as in the external circuit. So we just need to understand this as a normal electric circuit where the load is the electrolytic cell. And flow of charge takes place. It's just that the flow of charge is positive to one side and negative ions to the other side, making up the total current. All right. So what else now can we say here? Now, once the bromide ions now move to the anode, here they get rid of their electrons. They leave their electrons and they discharge. And the result is that here at the anode, now we have the production of bromine gas. So here we see bromine gas, and we're going to see bubbles. And we can see the gas actually because the bromine gas has a color. It's like a brownish orange. Here's the bromine gas, just to see how it looks like. We have seen before the colors of the various halides. So here's the bromine. This sphere has bromine gas inside. This is the color that we're going to see here produced at the anode. And here at the cathode, the lead ions will move to the cathode, and they will pick up electrons from the cathode, and they will discharge as well. And in fact, they deposit on the cathode. They make the cathode covered with lead. So this is what happens in the electrolysis. Now, if we notice carefully now, if we write down the half reactions that happen at the anode and the cathode, which is actually exchange of electrons, and where have we seen exchange of electrons? In the redox reactions. What happens here is a redox reaction actually, and that is why, another reason why the electrolysis is placed in the book after the redox reactions, because actually these are redox reactions that happen here in this electrolytic cell with the help of electricity rather than heating. Okay, here we have heating just to melt the lead bromide, not to help the reaction, but just to melt it. What helps the reaction is the electric current that we supply due to the battery that we connect. Now let's see what happens at the anode and the cathode more precisely, because we want to be interested in the redox reaction. So here I have it again all together. Now okay, I start from the cathode. Okay, so here's the cathode, the negative electrode. Okay. So at the cathode, we have the lead ions attracted to the cathode, and they pick up electrons from the cathode, and they become lead solid. deposited to the cathode. So here is this, this is a half reaction that concerns only lead. So here we have lead, look at this in liquid form because it's molten here. Lead ions pick up, each ion picks up two electrons from the cathode, and the result is the formation of lead metal. That is why it says solid. And you see, you can see here clearly that this is a reduction reaction, because from the oxidation, look at the oxidation state of lead from 2+, when it was an ion, from 2 + 2, let's say, it ends up with 0, because this is now an element and its oxidation state is 0. So it has been reduced. It's a reduction that takes place at the cathode. At the cathode, we always have reduction. And so reduction happens at the cathode. And how do we remember that? Red cut. You see this red cut? There is a reason why this is a red cut, to remind us that the reduction takes place at the cathode. Okay, reduction at the cathode, red cut. Now, at the anode, there's another half reaction where we have the bromide ions moving and leaving their electrons, which are these electrons now will continue in the external circuit. You see now the exchange of electrons in the whole circuit, isn't it? So there are no electrons moving here. The exchange of electrons happens at the surface of the electrodes, the two electrodes. And but inside the liquid, there are no electrons. There are only positive and negative ions. So anyway, here the bromide ions leave their electrons, and these electrons continue through the external circuit and they go to the other side. So what the reaction takes place here? We have the bromide ions becoming bromine element, gas, and leaving there at the anode the two electrons. So here we see that the bromine from the oxidation state of -1 ends up at 0, because this becomes an element with oxidation state 0. So it oxidizes, increases in oxidation number, so it's oxidation. So oxidation happens at the anode always. So how do we remember the oxidation here at the anode? We say this is an ox. We say an ox. To remind us. So there's the red cut and an ox to remind us of what happens. The oxidation happens at the anode and the reduction happens at the cathode. Okay. So maybe that will help us. I like the red cut and the ox. And if we put these two reactions together, because these are half reactions, half reaction at the anode, half at the cathode. If we write them together, where do I have them together? Anyway, that is the result only. Here, it could be like the lead ions and the bromide ions together, combine, and they give the lead solid and the bromine gas. This is actually the final reaction, the moral of the story that happens inside this electrolytic cell. This compound in molten state, this is liquid, with the help of electricity, breaks into its elements lead and bromine. This is the proper reaction. And we see that this is a redox reaction. And now, okay, so what we've seen today is what happens when we electrolyze a molten ionic compound. So next week, we're going to see what happens when we electrolyze a solution. Solutions, where it means aqueous solutions. Then we're going to see the role of the water. Here, there was no water. Be careful. This is molten. There's no water here. It's not a solution. There's no solvent and solute. It's just molten lead bromide. Okay. And the same applies to other molten ionic compounds. It's not just for the lead bromide, of course. Any ionic compound, if we melt it in an electrolytic cell with the help of electricity, it will break into its elements. And And guys, I hope this was understood, because next week we need to continue. If you have problems, you can just send me a message and we can revisit things that were not clear. Okay.